right, thank you so much. I will speak in English because it's easier for me. In this presentation, I wanted to point the attention on a few considerations that are considered often trivial, but I've seen in the last 15 to 20 years in California and many other places, a lot of mistakes in design and operations of microirrigation systems. So today I want to point the attention on a few things that are not trivial at all, especially when we are facing heat stress or drought and we don't have enough capacity on the microirrigation system. So I want to just to go through a few criteria and consideration for design of microirrigation systems and point on vineyard water management, vineyard water and energy requirements. And then I prepare a couple of calculation examples, but I'm not going to go through because of for the sake of time, but those are useful for you later on for calculating amount of water and energy that is needed for irrigating grapes. And I'll point out some recommendation for resource efficient irrigation system. I usually use the term resource efficient because it's not only a matter of water, but it's also a matter of energy. Energy is a big component in the budget now, especially after the energy crisis, the war between Russia and Ukraine. So we got, a very high cost of energy, especially when we pump water from the aquifer. And the aquifer is becoming, in this climate, extreme variability of weather and climate, the aquifer is becoming some sort of insurance policy for growers. So being resource efficient means being efficient in terms of water and energy, all right? So I wanted to give you some general understanding of what it takes to be resource efficient. First of all, everything starts with a good system design. It has to be somehow done by professionals that are skilled. We got one here. And has to be accurate. Doesn't have to be cookie cutter, as we say. Like the same concept applied regardless of the soil, regardless of the difference. And so, but you also have to consider a flexible operation, because during the economic life cycle of the vineyards or the orchard, we have to operate the system under different conditions. Then we have to have a proper installation, so a good experienced installer, and after we install, there's regular maintenance and somehow periodic system evaluation. All this stuff is always given for granted. Once you install a drip system, it's supposed to work at 95% distribution uniformity or efficiency for all its life. This is not the case. It depends on water quality, it depends on how the system is operated, it depends on the pumping system. So, I've seen a lot of drip irrigation system performing at 50% or 40% of application efficiency. It's very common in California that everything is given for granted, that the system performs well, and then we end up applying way less or way more of what we are thinking we are applying. Then, after the two blocks are cleared out, so you have a good system in place, you have a regular maintenance, and you have periodic system evaluation, you fix the problem, then you have to have somehow a kind of a defined irrigation strategy in mind, and this now has to be adaptive to the climate. So 1 year is drought, 1 year is wet, 1 year is average. So you have to have some sort of sense of how to apply water to your vineyards, and whether you're going to do full irrigation in wet year or we're going to do deficit irrigation. It could be sustained deficit irrigation, so below the potential, or regulated deficit irrigation, so apply less water during specific stage, or you want to apply homogeneously the water or site specifically because you got, So there are a lot of things that you have to consider in order to be efficient. Then you have to have some good irrigation scheduling, accounting. We saw examples of, satellite application. Mike gave a presentation on crop manage. So the scheduling is important, but then after the scheduling, you have to implement the schedule, all right? And then once you implement the schedule, there needs to be a feedback. So have I implemented the schedule according to what I want to achieve with my grapes or not? So this looks like a very difficult, pathway or route. But, we always focus on, let me show you. The first block is related to good design. The second block is related to good maintenance. And the third block is a good operation, right? We always focus our attention on scheduling, ET, and how much water the grapes has used. We always forget the first two, but if we don't know how much water our system applies, then the scheduling and the implementation is basically very kind of scrambled. We don't know. It happens every time we do a system evaluation that we get, inches per hour or millimeter per hour really applied by the system that are either way more or way less than the design. And it happens every time. So when we show the data, most of the time the farm managers say, no, this is not possible. We'll say, okay, let's repeat the measurement. And then that, is the case. So what I wanted to say is if you don't take care of in a good way of these two parts, all the rest is kind of scrambled. All the rest becomes problematic. So, the research over the last 20 years has shown that grapevine in a different growing condition has, a woody structure, kind of an anchorage of the plant, of the vines, and then he has like feeder roots that mine the soil in different directions. And so basically we got feeder roots that goes horizontally and laterally, and those roots don't stand water ponding. They don't like asphyxia or hypoxia, and so they thrive in unsaturated soil. So this is one of the reasons why somehow surface irrigation and sprinkler irrigation were abandoned in microirrigation and in vineyard management, and now more and more grapevine production is becoming precision irrigation with micro irrigation system. All right, so most of the time in most of the growing areas, so low volume micro irrigation, so drip and micro sprinkler are mostly used for grapevine. Surface and drip have resulted in somehow increased incidence of pest disease. So they are now being considered for other purposes. So like during winter for groundwater recharge, right? Or for leaching. When you have salty water, you have to leach, then drip is not so effective. And then, but for irrigation purposes, probably drip irrigation and micro sprinkler fan jets are among the best systems. So what are the aspect where to focus the attention? At the design stage, first of all, we have to somehow get a sense of what is the available water supply, type of soils, and how it varies across the vineyards, what's the slope, and what's the aspect. So it's north-facing, south-facing, if we have hillside terrain. What is the projected vine spacing? So the planting density and also the row orientation makes somehow a difference, because I show in the other session, that all depends on the amount of energy that the vine intercepts. So the amount of ET is depending on the interception. Also the trellis system that you project, over the future, what kind of trellis system you're going to grow, and the canopy size at full development. So those are aspects to be accounted for. So then we normally, when we design a maximum water application rate. So this is a millimeter per hour or inches per hour, and a maximum irrigation depth that your soil can stand, because you don't want to have deep percolation. You want all the water that you apply to be retained by your soil, right? And these are based on soil properties normally. So the water application rate doesn't have to exceed the infiltration rate, and the maximum irrigation depth doesn't have to exceed the water holding capacity of your soil. Otherwise, the design is basically useless. Because I've seen a lot of drip systems that after half an hour, they get ponding after the dripper, and that's basically a bad design, all right? So the first rule of thumb in design, so apply the peak daily ET or the water to somehow match the peak daily ET in less than 24 hours. Most of the systems that I've been dealing with in the past 20 years were designed for the lowest investment cost, the lower installation cost. So the maximum daily ET was designed for 24 hours. So the system gets broken or the pump gets broken, there's no time off to recover, to catch up. So a clear recommendation is shorten the operation of the system to 16 hours. So every day you got some time to catch up if something goes wrong. Then normally we size the different part of the system from downstream to upstream in order to somehow account for the flow rate, which is the maximum application rate and maximum irrigation depth. And we calculate the flow and friction losses along the pipe system, but we wanted to ensure the operation flexibility. Operation flexibility is something that I'm going to show here. So it means that the system must perform a high level for different range of operating conditions. So different level of pressure and different level of flow rate, right? So we want to be able to adjust the operation according to what we say, the various system loads. And so during the lifetime of the system, water needs of the small vines are small, and then they grow over time. So over time, we have higher flow rate, higher pressure that we need. Okay, block a different elevation with respect to the pump or different distance with respect to the water pond. Must be somehow sized for different level of pressure. Okay, so everything has to be accounted for. Block with different emitters because we might have different soils in different part of the farm. And so we need to account for different flow and different pressure, all right, for the different blocks. And sometimes we have composite system where we have, in areas that are sensitive to frost, we might have micro sprinkler for frost protection and drip for irrigation. So we need to balance that too. We need to make sure the system can operate for different flow and pressure and frequency as well. The aquifer level over time might fluctuate, so your system needs to be adjusting for this change in total head. What we are experiencing in California, there's a sharp decline in aquifer, so sometimes growers have to pull out the pump, increase the pump capacity, get a new pump or a new engine in order to accommodate something that was not designed for, because we have a progressive declining in the level of aquifer. The second rule of thumb, the application rate. This is completely, most of the time, is completely ignored by some designer. And so the application rate, so in millimeter per hour or inches per hour, must be way less than the basic infiltration rate. And the basic infiltration rate is not what you get at the beginning when the soil is dry. You have to wait until like a few hours until you get this level when the infiltration rate becomes constant. So that is your value. So you want to apply water in a way that is lower than the application rate, all right? And this is normally the application rate of the different type of systems. So those are general guidelines, but I also wanted to show you something else. So that, if we apply a micro sprinkler system where our basic infiltration rate is 0.02, we're going to have water ponding. And so we need to pulse irrigation on and off. Otherwise, you don't get water to penetrate. You create condition for asphyxia, lack of oxygen, water ponding. It's a lot of problems, all right? These are another table with general guidelines for the different type of soil and the different, different slopes. What is the recommended maximum application rate that you have to keep in mind when designing a system? So the steeper is the soil, the faster water runs, so there's less opportunity for the water to penetrate. So it means that the deeper is the slope, then you have to apply less and less and less water, so with lower application rate. And this is, again, general guidelines, but it's better to get a good sense of your soil when designing a system. This is always overlooked because basically nobody does, kind of a soil survey when, before designing. Most of the time the soil survey is done after designing when the problems are already there. And then you have to find a way to retrofit the system, all right? The third rule of thumb is the maximum applied water in inches should be, as I mentioned, way lower the water holding capacity, okay? And this is another table that I give you. Again, this is in inches per feet, but conversion it's easy. For the different type of soil, what type of water holding capacity range you have, and always, there's a kind of an average value for the different type of soil. So your maximum amount of water, that means your application rate multiplied by the number of hours of your application should not exceed this. Otherwise, you waste water and energy and nutrients, all right? So this is also important for operation. There's also ways now to assess the spatial variability of soil, and those are, with electromagnetic induction, you scan the soil and you somehow get a sense of the different in texture. You have to do in this survey under, kind of a field capacity after an abundant rain, and so you get a sense of the difference in texture. This is an example at Davis of a field that we scanned before doing a subsurface drip irrigation, before designing the subsurface drip irrigation, and we saw that there were like sharp difference between the zones. So then you decide, what's your criteria for the spacing of the line and the spacing of the emitters in order to avoid, shortage of water and to avoid excess of water. There's also methods to understand the properties of the soil before the mistake is done. And this is something that nobody actually does. There's a disc infiltrometer in order to understand how much water penetration you get over time. So 2 hours, 4 hours of irrigation, 6 hours, and also the water subbing laterally in order to know, this is also important for design and operation. So there's easy measurement before the mistake is done. And again, this is a disc infiltrometer. You measure the unsaturated hydraulic conductivity. You do a few samples and get a sense. The alternative is to lay down a dripper and operate for 2 hours, operate for 4 hours, and get a sense of how the wet area changes. But it takes more time, actually, to do the field test. So this is the criteria for calculating the maximum amount of water to apply to match DET. Then we're not looking at the soil. We're looking at maximum peak daily ET that we get from the crop. And then this is an example. Let's imagine that for some of the crop in California, the maximum daily ET is 0.20 inches. That means 5 millimeter per day. All right, and so normally we calculate the maximum amount of water to match that ET by using the maximum daily ET multiplied by irrigation interval and then divided by the efficiency of application. So that's an example that I ran for you, and let me see, probably. So that amount of water that we have to apply, maximum amount of water to match that ET, maximum daily ET, should be applied in less than 24 hours. Otherwise, you don't have time to recover for misworking or misoperation of the system, all right? The time for irrigation, the time for irrigation, it will be given by the maximum amount of water that you have to apply, 0.7. This is a design parameter, divided by the application rate. You want to make sure, again, that your application rate is less than the soil intake rate. So there's a few steps of rational calculation you have to do in order to make sure your system is going to be designed for, operate under the maximum condition, but also a flexibility of operation should be considered, all right? Now, we did this regardless of knowing the soil, but then we have to check whether this amount of water, 0.7 inch, is compatible with the soil. And this is what we normally do to make sure that that amount of water to match ET is compatible with the soil water holding capacity. And there's a few step calculation. If that amount of water exceeds the water holding capacity, then you shorten the interval. So instead of applying water every 3 days, then you shorten the interval. You apply less water, but every 2 days or every day, okay? And so you solve, the design problem in that way, okay? And so this is another calculation example. Here at the end of the story, I think there's another example that I prepare. So now the question is how to convert ET into amount of water in liter per vine or gallon per vine. And then if you have the English unit, you multiply that ET in inches per day, multiply the crop spacing, so plant spacing between the vines, multiply by this 0.6 coefficient. If you use metric units, you just apply the multiplication between the amount of ET that you have to satisfy, multiply the crop spacing, okay? So that converts the ET into gallon per vine or liters per vine. And this is a table that is in one of the manual of the University of California. It's in inches per day and multiply it by the crop spacing. And so it gives you an idea of the number of gallon per plant that you have to apply for different ET level. Here's the example that I did. And Cabernet Sauvignon, 5 feet by 6 feet, VSP trellis, single drip line, root zone 5 feet, and then effective root depth is 70% of 5 feet, and then wetted area somehow at 0.25 or 25%. At the end of the story, the maximum amount of water to apply is 0.8 inches and corresponds to 15 gallons per vine. And following that calculations that I run before, you're gonna get this presentation. So typical flow rates and pressure of drip and micro sprinkler it varies between 0.5 and 30 gallons per hour at the operating pressure 20 to 35 psi. The emitters don't require all this amount of pressure, but most of the time, we have filter, and the filter is a basic component that requires additional pressure with respect to the emitters, all right? Especially when they have back flushing capacity. So, you have to consider all this pressure in order to size your pump. The most relevant system components are normally the flow meter, because you can spot easily if you have a leak or if you have a clogging with respect to a flow that the system should allow in normal operating condition, and also the pressure meter, so the pressure gauge, okay, in different critical points. Those are the most relevant system component to troubleshoot. So never forget the flow meter. The flow meter is probably the most important part of an irrigation system. In some cases, we need to put pressure regulators at the beginning of each line, especially when we have undulating terrain, because you might want to normalize the inlet pressure into the drip line when you have this type of undulating terrain. So you want to make sure that you normalize so the flow doesn't change so much with respect to the inlet pressure. So those pressure regulators stabilize the pressure in order to normalize the flow along the line. Water requirements of grapevine. Normally in California, it varies depending on the area, depending on the weather condition, whether it's coast or inland, between 400 and 700 millimeter per season. I'm done almost. And this water can come from different sources. The soil moisture residual from the winter and irrigation. And sometime in a coastal area, you get fog and dew. That's an additional source of water. It's water contained in the air. It doesn't evapotranspire from the soil, but somehow there's a dew fall on the vegetation and on the ground. So that's water that contributes to evapotranspiration. Energy requirement. Probably this is my last slide. You can calculate how much energy you need per your vineyard, and this is in English unit, but the conversion it's easy. It takes normally 1.37 water horsepower per acre foot of water per foot of lift. Okay, so that's pretty standard. So, and the different source of power, electricity, gas, diesel, propane, those are the characteristic output, okay? So, for instance, 1 kilowatt hour of electricity is able to provide 0.885 water horsepower per hour. From this, you can calculate the amount of energy required to lift the water. So, by doing your hydraulic calculation, you get a sense of how much energy you're gonna use and how much money you're gonna spend per energy. And I think this is taken from the Nebraska pumping plant performance criteria. It's considered somehow standard reference for the United States. I want to show you one more thing. I think I developed an additional example in this presentation to calculate the energy needs for micro sprinkler and drip irrigated vineyard. And I calculated total dynamic head of micro sprinkler, 180 feet. The total dynamic head of drip irrigation, 158 feet, because there's less pressure needed by drip. And the total acre foot of water to irrigate and to match ET. I think ET seasonal is 18 inches here. And the amount of, I did it for diesel power pump. And so I calculated everything, and it comes that the micro sprinkler will need 1,368 gallon per acre, and an amount of money that is $8,000. And in drip is way less because you're pushing water less, you're pressurizing water less. And I think the last thing that I want to mention is a lot of systems and provider of energy now is moving to the time of use. So it's like, imagine you have a Tesla or a hybrid car, depending when you plug it in, the energy rate, the price of energy will change. So the criteria now in California for designing irrigation system, because the energy is the highest cost for growers, is to go around the high peak rates, all right? So for instance, let's look at this very quickly. And so you have a very low rate until noon, and then from noon to 6 p.m. is the highest rate. So if you need to irrigate for 24 hours because your system was designed for the lowest cost, investment cost, you're going to spend a lot of energy because you have to run it anyway for 24 hours to match ET. If the soil allows, you can increase the capacity and apply that amount of water in a shorter time, and that will lower down your energy bill quite a bit. So a lot of growers now are designing the system in order to increase the capacity by 20, 25, 30% and lower down the cost of energy. So the real cost for 20 years vineyards or 25-year vineyard is not the investment cost of today, is what you're going to pay for the 25 years to operate the system. So if you're smart, you might want to do something like this and increase the capacity if the soil allows for having an energy efficient system. And when you somehow automate the system, you can start and stop depending on the time of use and depending on, so this is going to be, in California, it's going to be like this. You know, you have off-peak from midnight to 6 a.m., and there's a partial peak, and there's a peak during the day. Those are energy rates that are increasing. So your system should be irrigating here to reduce the energy cost. And if you have automation, you can do that. If you have manual, so nobody goes there at midnight, open and close, so consider also the automation. I think with that, I'll stop here, and sorry for overflowing.